So we were discussing the Hawking effect. This is the fifth class of this chapter, but we are very close to the end. So I will not finish it today, but I will only need half more class. And I will have to stop somewhere because we could keep discussing aspects of the Hawking effect for the whole year. So, but I think it was important. I find it important to see at least once the derivation in detail. This is why it took me so some time. So remember that we have this very simple model of gravitational collapse in which the black hole is produced by a shock wave of incoming radiation that produces the black hole. So we have the space-time in just Minkowski together with Schwarzschild. The metric is not smooth, but we can easily change the radiation to make it smooth. And we moved to the quantum theory, and we had two Fock representations, what we call the in and the int-out representation. The in representation is the representation associated with choosing as our basis for the space of classical solutions modes which are of definite frequency in Scri minus. So the positive frequency in modes, they are just of this type times the angular variables, and that gives us the info representation. We have a vacuum which, at the Scri class is indistinguishable from the Minkowski vacuum in this room. And there is a well-defined notion of particle, and these modes describe those particles. An alternative quantization is given by the in and out representation, which is choosing this Scri class together with the horizon as a Cauchy hypersurface. It's made of two parts. One is the out Fock representation, which is made using the basis of natural positive frequency modes in a Scri class, and the in representation, which is choosing some basis of modes here. Remember, there is no canonical or preferred notion of positive frequency there, because the horizon is the geometry is changing with time. Here the curvature is flat, and here it's not flat, so there's no time-like Killing vector field in that region helping us to choose that thing. So our choice was just for mathematical convenience. We make a choice, but keep in mind that it doesn't make much sense to talk about particles close to the horizon, because there is not really an ambiguous notion of particle. In Scri minus and Scri plus, there is. So we made some choice, and we construct this representation. And we realized that so what we wanted to do is to relate these two representations. And we know that in order to do that, all what we have to do is to compute the classical Bogoliubov coefficients. They are purely classical, but they contain information of the relation between the two representations. And this is what we did last day. We focus on modes reaching a Scri class at very late time, because this is where the Bogoliubov coefficients are non-trivial. So we focus on modes which will reach a Scri class at late times, late U out, and that therefore when you propagate them backwards in time, they are close to the equation. And the last thing I wrote was those Bogoliubov coefficients. So we have two bases: the basis of in modes and the basis of int and out modes. And we found, in fact, I didn't obtain the Bogoliubov coefficients explicitly. All what I did was to find relations between them, and we know from previous chapter that that is enough for our purposes, as we will see today. I don't know why I'm writing improvement. This is the out, alpha and beta. And there is also a relation between the int and out Bogoliubov coefficients. Int minus e to the minus 2 rs 2 pi Schwarzschild radius omega out. Remember that alpha and beta int are relating this with this. This is the alpha int and beta int. And alpha and beta out are relating that. I don't write L and M numbers because they are just proportional to the delta L, L prime, delta M, M prime, so I just go right to this. And this is the last thing that we wrote last day, and what we want today is to start working from that. So if you have any questions. So I want to move to the last subsection of this section. It's called 2.4. It's called thermality. And what I want to say here is that, let me see if I gave any number to the questions. Those equations are called 15. What I want to say here is that the relation 15 are identical to the ones found in the analysis of the Unruh effect. If we make the following replacements. Remember, in the Unruh effect, what we had was the right Riller wedge, or left Riller wedge, the Minkowski-Fock representation, the left cross right Fock representation, and we had the Bogoliubov coefficients. Here, these relations are completely analog to the ones we found here with the replacement Minkowski. Whenever we found Minkowski, we replace it by in. Whatever we had left, we replace it by int. Right by out. And the acceleration, we have to replace it by 2 pi over kappa. By 1 over twice the Schwarzschild radius, which is 1 over kappa. Remember that kappa was the surface gravity of a black hole, and we work it out. A black hole in a stationary black hole has a surface gravity 1 over 4 times the mass in appropriate units. With those changes, all the analysis that we do for the Unruh effect applies here. So we don't have to do the analysis again. We just have to copy the result and make those changes. In the Minkowski, in the Unruh effect, we had a global vacuum defined everywhere. That is the Minkowski vacuum. Here we have the in vacuum, which is defined everywhere, inside and outside the black hole. And we had the Riller observer, which only sees part of the spacetime. Here we have the out observer, which only sees part of the spacetime, doesn't have access to the horizon. But you know, right together with L, they reproduce the whole spacetime. Here, out together with int, they reproduce the whole spacetime. So it's completely analog. So therefore, we can read from chapter 5 the expression for the in vacuum in the in cross out focus space. So as I said, we don't need to do the computation again. Just go there and do those changes. And what we're saying is that when you take the in vacuum, which is naturally defined in the in representation, and you bring it to this other representation with the corresponding unitary operator. Then what you find is you have n, which is a normalization factor, I will write in a second, exponential of 1 over 2h bar, sum over L, m, integral in frequency, e to the minus pi omega kappa. Sorry, there is not a pi. There is, sorry. Yes, e to the minus pi omega kappa. A int dagger omega ln. Everything is in the exponent. A out dagger omega ln. I close the exponent, multiplying the int cross the out bracket. This is what we obtain. So it's again is an exponential of two particle states. In the Unruh effect, we had here left and right. Now we have in and out. And you can already imagine what are the consequences. This can be also written as follows. Multiplication for all numbers. This is a weird multiplication because omega is continuous number. But you know, if we use wave packets, that omega is replaced by a discrete index, and this is what I really mean by that packet. So if you want, this expression is a formal sum from n equal to infinity, 0 to infinity, e to the minus n pi omega over kappa, a state with n quanta with those quantum numbers in the in representation, a similar state in the out representation. So I just have expanded the exponential. This is all what I have done. And this, as you can imagine, is a quite important expression. And I'm sure you can read already the physics from it. Remember where n is a normalization factor. That can be formally written as, and remember I say formally because that state is really not normalizable. If I could take that. So this expression again tells us that the in vacuum in the int out representation is precisely a linear combination of states with an even number of quanta. You know, it's a sum of states which have an even number of quanta, half of which belong to the int sub-Fock space, and the other half to the out Fock space. And they are, it is said that there is a precise correlation between modes in the int, quanta in the int and out Fock space, as we saw for the Unruh effect. So the in vacuum is a combination of correlated pairs of quanta one element of the pair belonging to the in focus space, the other to the out focus space. Surprisingly, quanta reaching, so particles reaching Scray plus are uncorrelated between themselves. You don't find here correlations between out modes. For the same reason, quanta reaching, falling inside the horizon, they are uncorrelated among themselves. But these guys and these guys are correlated in a precise way, given by these correlations. So out, so quanta reaching Scray plus are uncorrelated. Quanta reaching the horizon are uncorrelated. But every single quanta reaching Scray plus is precisely correlated with a quanta falling across the horizon. This is what this expression tells us. It's exactly the same as we did in the Unruh thing.
So you can, it makes an intuitive sense why there's an exact matching in the Unruh effect, because there's a symmetry between the two spaces.
Mm-hmm.
They're essentially the same, but Scray plus and the horizon are different.
Right, right.
So
That is a very good question. And remember that, you know, that in the horizon there is really no preferred choice of basis. So had I chosen a different basis in the horizon for the in modes, I wouldn't have obtained this clean one-to-one correlation. But, you know, I choose that basis that makes these correlations just one-to-one. You know, if you choose a different basis for the in modes, you will find correlation, but not one-to-one. You will find that out modes, which are well defined, are correlated with a bunch of modes falling inside the horizon. But because I have freedom in the in basis, I have chosen the basis which diagonalize the correlations. Even more, you can see how I have done it. You know, I wrote the in basis, and initially when I wrote it, I didn't have any motivation, and the expression was kind of weird. But then, in the next day, I took the out modes and I propagated them backwards in time. And if you see the expression for the time out modes propagated, you know, modes from here to here, modes that reach Scray minus here are coming from Scray plus, when you propagate backwards in time. This guy here, this guy here. Modes that are in modes, they, when propagated backwards in time, they reach this section of Scray minus. If you see the expression for the out modes after propagation backwards in time, and you see the expression for the in modes, that I was choosing is just you know, a continuation of that. So here there is really a symmetry between this part and this part. And when you put the out and in modes there, you can realize that my choice for in modes was just the image of those guys, similarly to what we did in the Unruh thing. So mathematically, I was using that property. Of course, there is a choice. I mean, there is no preferred basis at the horizon. I could have chosen a different choice. Then this correlation will not be one-to-one. Will be one to a bunch of them. But you know, I think pedagogically it's nice to choose just the basis which diagonalizes the correlation to really, you know, because this really makes manifest that wherever it goes to Scray plus is entangled with the stuff falling inside the black hole horizon. I mean, this is very important. I don't insist more because I have repeated it for the Umbro effect and it's exactly the same, so I don't want to be too repetitive. And normally this is not the way that you find Hawking radiation in books. In some books you can find it. I mean, of course, this is not my derivation. But in most books, what you find is just the expectation value of the out number operator in the in vacuum. This is all what you find. And I will complete that. But you know, this is much more. This is exactly the in state in the in out focus space. And you can see all these correlations. You are looking inside the in state and see what are those correlations. From here, I can compute whatever you want. In particular, I will compute the number of out quanta in the in vacuum in a second. So even though this for some students is more abstract, because if you are not used to this quantum entanglement and it takes you a while to realize why I say that there is entanglement, but if you sit down and you work, you will see why there is entanglement. But I think it is a very nice expression. Of course, this is, remember, all this is true for modes which reach Scray class at late times. I am focusing all the time in modes which reach Scray class at late times. Now, from the viewpoint of an observer at the Scray class, you know, the relevant information in that state, the relevant information in the in state can be obtained by tracing out the int degrees of freedom. The degrees of freedom associated with in modes. You know, for a guy in a Scray class, he doesn't have access to the degrees of freedom associated with the in modes, because these are guys which have support inside the black hole, and the Scray class is causally disconnected from the black hole region. So for a guy in a Scray class, for a guy here in a Scray class, you know, he can just get rid of the degrees of freedom inside the black hole, and you know, and that is the relevant information for him. All the other information here is irrelevant for him. So what we have to do is to take this step and project it on the out Hilbert space. So if you want, take a partial trace with respect to the in degrees of freedom. So remove them. Again, the same as we did for the Unruh effect. So again, repeating the derivation of section 5.3. The resulting state what do you think is going to be? So it's first of all a mixed state. It's not pure. That state is pure. When you take partial trace with respect to in modes, you get a mixed state, and that is precisely the definition of entanglement. You know, choose subsystem of a system in a given quantum state is entangled if you take a pure state and you remove half of the degree of freedom and you get a mixed state. This is because you're removing part of the information. So is a mixed state characterized by a thermal density matrix. I don't do the derivation in detail because it just copies what we did in chapter 3. At a temperature I call Hawking temperature, and it's going to be the same temperature as that we obtain in the Unruh effect, just replacing A by 1 over the surface gravity of the black hole. So it is h bar, put in all the constants, kappa, which plays the role of the acceleration, 2 pi, and the Boltzmann constant. If you write kappa, remember kappa is 1 over 4 times the mass of the black hole. This is 8 pi g, Boltzmann constant, the mass of the black hole. And if you want to put the speed of light would come here. Normally I put it equal to 1, but now let me just put it explicitly. This is the celebrated Hawking. Hawking temperature. As you imagine, it is difficult to exaggerate the importance of this equation. First of all, I believe this formula is extremely beautiful. You know, I have never seen before a expression with all these fundamental constants together. Has to do with special relativity, has to do with quantum mechanics, with gravity, with statistical mechanics. So all the 4 fundamental constants are encoded in a single formula. So this physics, the physics behind this is, you know, is a precise connection between all these different things. Again, quantum mechanics, gravity, special relativity, and thermodynamics or statistical mechanics. Quite impressive. And the physical consequences are just sequences are simply atomic. So physically, the result of this computation is interpreted as if you have a black hole, what is going to be formed by gravitational collapse. Before the black hole, you take the field and you prepare it in the vacuum state. The black hole gets produced by gravitational collapse. You wait long enough and you go really far from the black hole. And if you see the black hole, you will see a flux of thermal radiation coming out from the black hole. You know, the black hole will be like emitting particles with a thermal spectrum precisely at this temperature.
So in the derivation, we purposefully took a case in which the black hole is being formed. Right. So does that mean that all this radiation comes from only that process? If any radiation goes close to the horizon after the black hole is formed and goes away, that wouldn't be like this. This radiation is just coming from the process of forming the black hole?
This is just it's a consequence of the dynamical.
So all this
evolution.
radiation was
All this radiation
at that time when the black hole was formed?
I didn't say at which time and where it's produced. The only thing I have said is that a guy in a straight class will see that radiation. This is my only statement. You know, I haven't said anything else. You know, where, when it's produced, you know,
Straight class
asking is
is
like,
like very infinitely far away, right?
and you know, and you cannot, like, it's not a well-posed question. It's like, where is the electron in an atom? You know, it's a quantum
No,
mechanical
but there's
thing.
a reason why we took a dynamic case. If you said that if we had a black hole already, then we wouldn't have this.
Right, there is
So, so this essentially has to do with
the dynamical process.
Yeah.
Right. But exactly. So dynamical collapse is crucial here. You need a horizon which was not present before and has been produced by gravitational
So
collapse.
yeah, that thing has.
That is what produces Hawking radiation. Right. Essentially, you know, I mean, the idea is always the same. Mathematically, it's always the same. That you have an initial state which is defined in the whole space-time, the in state, And suddenly something happens, and the observer only has access to half of that, or a portion of that space-time. Therefore, all the correlations between here and here that the initial state has are lost for this guy. And what was a pure state becomes a mixed state and full of quanta. No, the information paradox is related to that. But it's very closely related. I say no, but no, it's half a yes. So yes and something else. So let me go to that. So the physical consequences of explanation. So just writing this computation in physical terms, this is telling to us that, you know, if a real scalar field is prepared in the vacuum before the process of black hole formation, then an observer located far away from the black hole at late times after the black hole has been formed will observe that the state of the field is a thermal state of outgoing radiation at the Hawking temperature. So this is what this calculation is telling to us.
Is it true for fermions too?
Yes. But you need a thermal fermionic distribution, Fermi-Dirac distribution, which has a minus somewhere.
Right.
You know, remember that, you know, the problem is very similar to the problem that we discussed for a singular harmonic oscillator, which is time dependent, and the frequency is constant in the past and constant in the future, but changes in the middle. Remember, we put the oscillator in the vacuum state initially. There is a well-defined neutron vacuum. We go from our lab, the frequency changes with time, we come back later time, and the vacuum initial state has become a state full of particles. Exactly the same is happening here. The only thing is that, in addition, there is an event horizon that makes that, you know, whatever you see has exactly a thermal spectrum. But it's precisely that. And physically, this is what is going to happen. You know, if you go to a black hole in our galaxy and you do the detector, you should see Hawking radiation coming out from the black hole. So black holes are not black anymore. You know, it's not true that black holes are black. I'm not saying that the radiation comes from the horizon and reaches to me. I am just saying that if you put a detector in a straight glass, you will measure radiation.
That answers that question. I was going to say, is that true? That's true infinitely far away from the black hole,
Exactly.
right?
This is what I have said.
So that's not red, so there's no redshift.
There is, I mean, there is no pretty, but I mean, you could then ask what happens if I trace these particles back, they will increase energy, etc. But the, you know, our computation just tells us that in straight glass, you will see that.
Yeah.
I mean, your point is very well taken, and it's what people call the trans-Planckian problem, and it's a good question. But you know, really, the Hawking derivation solely makes reference to a straight glass, to what you will see far from the black hole. And extrapolations are very dangerous. You know, this picture that you have a black hole, and there is a pair of particles, one falls inside the black hole, this one, the other one escapes infinity. I mean, that is extremely heuristic. first of all, I don't know what you mean by particles inside the horizon. It's close to the horizon. There is no good definition of particles, and nobody in this computation we saw that you know it's just a heuristic picture that people, even Hawking, uses to talk to the general public.
This firewall or something like when people discuss something like that.
That is related to this, but it's not the it's something. So never use this picture. If you talk to your nephew, that you are allowed to use this picture. But if you talk to a physicist, you are not allowed to use this picture. And I don't know what you mean by particles close to the horizon that two are produced, one goes. Nowhere in this computation that happened. Just this computation tells us that the in vacuum, that is the same. The in vacuum happens to be a thermal state here correlated with some quanta going inside the black hole horizon. So I don't say what happens in the middle. I didn't say that. I just say that in that Hilbert space, the in vacuum happens to be a thermal state here with correlated with quanta there. That's all what I have said. The quanta there, of course, are ambiguous. I could change bases. I don't have a preferred choice for bases. It's true that if I choose a mathematical one, I have diagonal correlation. But I could choose another one. In a straight class, I have a preferred basis, and therefore I talk about Hawking particles in a straight class. Some people call these guys the Hawking partners. But, what you see is correlated with something in the horizon. But it's not something that not something that was created together and they fly away. No. The correlations are between here and here. This is just a Cauchy hypersurface, and 2 points in that Cauchy hypersurface. The vacuum is correlated with this point.
The effect is strongest close to the horizon on that diagram, right? So
Right.
Hawking
radiations are ICC, which are modes that if you trace back them in time, they are infinitely close to the horizon.
So it's close to the horizon in the sense of having passed by the horizon, or
having the classical mode functions, solutions to the wave equation that you use to describe out quanta, if you trace them backward in time, the ones that for which you see Hawking radiation, they go infinitely close to the horizon in the past. This other picture where you have the star collapsing and a horizon forming, they are modes which are extremely close to here, and they reach a straight class in the future, but they are extremely close to the horizon.
okay, but
don't think them as particles coming from there. They are just the solutions that you use to write your basis of functions.
right. But this picture also doesn't show us the dynamics of the black hole evaporating, right? So we can't think about it as being when the black hole evaporates.
Right.
either.
At this point, no, but that is an unavoidable consequence.
Right.
Because
Okay.
as I will describe, you will see that these particles carry energy, and that energy has to come from the black hole. There's no other way. So the black hole needs to evaporate by Hawking radiation. In fact, if you compute the energy momentum tensor of the in vacuum close to the black hole, you will see that there is a negative flux of energy going in the black hole and positive going. The computations of the energy momentum tensor, which are very difficult, are only known explicitly analytically in 2 dimensions. You have a flux of energy here, positive, and a negative flux of energy going down. Globally, energy is conserved, but whatever you are losing here, there we have. And this is the celebrated Hawking effect. Which is, as you can see, a remarkable result in many sense in theoretical physics and in gravity. And still people is trying to understand what is going on 40 years after Hawking. The amount of physics that this equation is encoding is huge. Comments, just repeating what I have said. Just to emphasize it again, Hawking quanta at the scrape glass are uncorrelated among themselves. but correlated with degrees of freedom falling into the horizon, falling into the black hole. Second, from the state that is great class, I forgot to mention the name, but repeating derivation, the resulting state, I was going to call it rho H. In the Unruh effect, I was calling it rho U. That is just the mixed state that you get at the straight class from the in vacuum after tracing out the int degrees of freedom. It's a thermal density matrix. But from that state, we can derive any observable. At the straight class, any physical quantity at the straight class is going to be derived from the thermal density matrix that we obtained. A typical one is the expectation value of the out number operator. For instance, the number operator associated with out quanta with frequency omega. So that will be A out dagger omega L M A out omega Lm. So what is the expectation value of that operator? That tells me directly how many quanta you are expected to measure if you are in a straight class with a detector. In fact, this expectation value is what normally is presented as the derivation of Hawking radiation, and is in fact what Hawking obtained. Hawking didn't obtain this expression in this way. Hawking just obtained the expectation value of that number operator. And 1 year later, I think Wald and Parker independently they obtained something like that. So we have to compute that expectation value. Let me just compute it from rho. So do you remember how to compute expectation values from a density matrix?
Trace of operator time.
Take the trace of the operator times H. And we know, I don't need even to do the computation. We know from previous analysis that this is going to be given by the sum of the volume of coefficients. And there is a trick to compute this easily. To compute this. The trick is the following. First, from the properties, this is out. Sorry, this is out. From the properties of alpha and beta, we know that, this must be equal to 1. Normally we see this expression with different indices, something like sum over j of j I alpha conjugated something like k I minus beta equal to the delta ij, but if you put j and k together, you get this expression. So this is just a particular case of the more generic expression. But this is all what I need. I want to use that, and using now relation that I wrote before, relation 15, or one of the relations 15. Remember, we related, I wrote it before, a relation between alpha out and beta out. And if you take absolute value of what I wrote, you get this. In what I wrote, I didn't have absolute values, but I had here a phase. So if you take absolute values, the phase goes away. With these two expressions, it is trivial to compute what we need, because, you know, because from here, just using that, we obtain that this is going to be e to the 2 pi omega over kappa minus 1. So I can take common factor of the out. It's squared, so I need a 4 here. There was no 4, no 2 here, sorry. Or there was, now I don't remember. There was no 2 here, so I have to put a 2 because here everything is squared. And this doesn't depend on omega prime, so this is equal to 1. This doesn't depend on omega prime, so it can go out of the integral. So from here, I obtain directly that the integral that I am looking for, that integral, is given by 1 e to the 2 pi omega divided by kappa minus 1, which is precisely 1 over e to the omega h bar divided by Hawking temperature minus 1. And this is what we call a Planckian spectrum. Planckian spectrum for bosons. You know, the out observer, if he tries to measure the number of out quanta, he will observe a Planckian spectrum, of course, because we just said that the state is thermal. This is what Hawking obtained. And he therefore said that the state is a thermal state. But you know, if you are very picky, you can say, no, I mean, you cannot assume from a single expectation value, you cannot conclude that the state is thermal. I'm sure that you can cook out some density matrix which reproduces this expectation value, but it's not thermal. But immediately, Walt and Parker and other people, they show that the state is exactly thermal. Not only the number of quanta agrees with the thermal spectrum, but any other expectation value will agree with the thermal spectrum. If you have fermions, you have a class here. So you know the number of quanta in bosons can be as small as you want. When omega goes to 0, the denominator goes to 0. So the number of bosons in a thermal distribution with very low frequency is exponentially large. For fermions, that is not true. You have a class here, and you have a maximum number of fermions, which is 1. And of course, you know, these particles that you observe in a straight class, they carry energy. They carry energy given by this. This is the number of particles you multiply by the energy of a single particle, h bar omega, and that is the energy that you are obtaining. And therefore, the black hole must lose mass and must evaporate. And as you can see, you know, the typical wavelength of particles in Hawking radiation is of the order of the mass of the black hole, you know, or the surface gravity. So it's of the order of 1 over m, the mass of the black hole. Of course, it's the only scale that you have. You know, the Hawking temperature is given by the mass of the black hole. 1 over the mass of the black hole. That is very important. Typically, the dominant wavelength in the Planckian spectrum is given by the scale Schwarzschild radius of Jupiter, which is Schwarzschild radius, except numerical factors. Dimensionally, I need G to have a length if C is equivalent. I mean, I don't know if you can put in Hawking's mind at that time. He was the guy who wrote in the early 70s, the area law, that the area of an event horizon grows always with time in GR. He was deeply involved in the paper of the other laws for the black hole mechanics, and probably he was pushing this thermodynamical analogy a lot. But the temperature of a classical black hole is 0. And then himself, the same Hawking, he did this computation. Quantum mechanics, completely different computation. Quantum field theory on the space of a black hole. And he obtained that once you put quantum mechanics, the black hole radiates as a black body. So this is something really, really big. Let's put numbers. Probably with these numbers, Hawking wasn't that happy. Otherwise, he could have already the Nobel Prize. If you put numbers in the Hawking temperature, you put the value of all constants, you are going to 10 to the minus 7 in Kelvin. So temperature is proportional to 1 over the mass. Therefore, a black hole of 3 solar masses, is 3 times to the minus 7 Kelvin. That will be the temperature. So is 7 orders of magnitude cooler than the CMB.
Temperature is proportional to the mass or inversely proportional?
Inverse proportional. This is the mass of the solar mass.
Okay.
So it's a constant, 1 over m.
Okay.
So you can see that here, 1 over m. The only quantity here is m. The other are constants.
Okay.
So the only scale in the Hawking temperature is the mass, and is 1 over m, the temperature. And that is
I think I misheard you, sorry.
Sorry?
I think I misheard you, sorry.
That's right. Of magnitude, 7 orders of magnitude cooler than the CMB. CMB is 3 kelvins, so physical black holes, which are at least 3 solar masses or bigger, the temperature is extremely slow. We cannot detect Hawking temperature from astrophysical black hole because the CMB is hotter than that. So the CMB will eclipse.
Even if we have something in the galactic center, the galaxies all around.
Right, and the galactic center that has millions of solar masses, that will be millions of times more than that. So temperature will be 10 to the minus 20 Kelvin or minus 15 Kelvin.
So you need a micro black hole.
There is no way. But the good thing is that pH is proportional to 1 over the mass, and that is the good. So if the holes evaporate, they lose mass, they become hotter. They lose more mass, they become hotter. So black hole evaporation is explosive. So the more they emit, the more they heat up. And this is quite remarkable. Unfortunately, all black holes, all astrophysical black holes in the universe, they are not evaporating because the CMB is hotter, so they are absorbing more than they emit, so they are still growing in mass. We have to wait until the CMB cools down by the expansion of the universe. So at some point, the CMB will be cooler than the black hole, and the black hole will start losing mass. But so far, astrophysical black holes are still winning mass, getting mass from the CMB. Only if there are what people call primordial black holes, we could see Hawking radiation. Primordial black holes are, Hawking had. I think the title of his Nature paper was Black Hole Explosions, because he had in mind this. And he said that, astrophysical black holes are hopeless to observe, but, during inflation, in the very early universe, when the inhomogeneities of the universe were produced by quantum fluctuations, you may have some quantum fluctuations or some density perturbations which are too large compared to the rest, and they collapse and form a mini black hole. Those mini black holes, they have masses of 10 to the 14 grams or something like that, so they are not too massive as compared to a star, and they should be ending the evaporation process right now. So Hawking proposed to look at the sky, and if we see some kind of bursts of energy, that may be due to the end of evaporation of these primordial black holes. We haven't seen that. So that implies that A, this is wrong, or I don't think is the case, because this has been tested by many different things, or B, that primordial black holes were never formed, or were forming a rate much lower than what we can observe.
So there's a particular, it's a black body spectrum that we're looking for, bursts of black body spectrum.
Some black body spectrum.
Okay, so not like a gamma ray burst or like a...
I mean, in principle, it has to be dominated by black body spectrum, except at the very end of the evaporation, which we don't really know what will happen.
Right.
But there is nothing that agrees with what we expect. So there are many, upper bounds to the number of primordial black holes formed. Okay. Have questions?
I forgot what kappa was.
Kappa is the surface gravity. Kappa is 1/4m times g, and has to do with the heuristically with the intensity of the gravitational field, or with the acceleration, gravitational acceleration on the top of the. It's just a shorthand for 1/4m, or 1/2 the Schwarzschild radius.
I have a quick question, which may be dumb, but I'm kind of trying to figure it out. I kind of understand Hawking radiation from the point that far away from the black hole, I have a well-defined notion of particle, very much towards inside the black hole. I have a well-defined notion, and then when I have a Goldilocks transformation from one to another, I see that the vacuum over there really has particles here. But in thinking about it that way, I'm not imagining the black hole losing mass via radiation in a traditional sense.
Right.
Is the black hole shooting out? I'm unsure of how the black hole evaporates, since I have this somewhat arbitrary notion of what my definition of particles is.
Right. So, because we try to create this picture in terms of particles, that you have particles arriving to us, and therefore the black hole should emit them. But close to the horizon, there is no well-defined notion of particle. You can say, yes, there are particles going outside from the horizon, and I can say, no, there are no. Look at my detector, doesn't mention anything. So who is right? So it's a bit of meaningless question. Only in the asymptotic region we can agree on particles. But we all will agree in what the energy momentum tensor is. You go and you compute T mu on the in vacuum, which is the state of the field. And we all will agree on that. That doesn't rely in any particle interpretation, in any closed basis. That is just a fully covariant quantity in any sense. And we can see what is this in a straight class. If you do the computation, it corresponds to the particles, the energy carried by this. So it's non-zero, and it's equal to a flux of thermal radiation going to the straight class.
We can be certain that the black hole is evaporating.
No, but you compute this in the horizon, and it's negative. So you have a negative. In quantum mechanics, the energy momentum tensor can be negative. Energy density can be negative in quantum field theory. So you see that there is a flux of negative radiation going there. So the black hole needs to lose mass.
Okay.
So would you say that is because?
But that's well defined at the event horizon.
That is perfectly well defined.
And we see that there's negative energy flux going in there. So
and this is observer independent. Every observer could agree on that because it's a tensor, it's an energy momentum tensor. So no doubt. If you tell me this is because particles come out from the horizon, I would say, what do you mean by particles? I don't even know what that question means. But energy momentum tensor is negative inside the horizon. So negative flags, positive flags there. It's a hole, Cauchy hypersurface, so energy is conserved because what you win somewhere you gain in the other side. That the black hole loses mass and at the expenses of radiating Hawking radiation. Most of the the cheap discussions in Hawking radiation is because one pushes this picture of particles beyond what you should. So you will see even that in papers, where particles come from. Well, in my opinion, not all, but most of the discussions are just empty because I don't know what you mean by particles. Even there are papers by prominent people about this tunneling effect of Hawking radiation. Computing Hawking radiation by tunneling of particle-antiparticle created inside, and one tunnels out, and they recover this kind of. And that has a lot of citations, but to me, I don't understand that because to me they are heuristic derivations, and one has to be careful with that. They have some utility that not complete. So rigorously speaking, you can only talk about particles getting to escape gas, and Hawking told us that the state is a thermal state there for those particles, and energy momentum tensor negative crossing the horizon and positive in escape gas. So black hole evaporation that is what that was.
Is it appropriate to say that the fact that you do measure radiation at Scribe Plus is directly related to the fact that the black hole has negative energy flux going inside it?
I mean, the energy cannot come from anywhere else.
I suppose I'm just initially was baffled by it because it's hard for me to relate a Bogoliubov transformation, which is what to me exactly where I know these particles are coming from, with a physical process or energy conservation. To me, that's just changing a basis, and suddenly I see particles. So I wasn't yet immediately comfortable saying, oh, that's due to energy conservation or something.
But take the example of this singular harmonic oscillator with independent frequency. And we agreed that you leave it in the vacuum, you come back later on, and there are particles. And everybody in the room would say, there are particles, look at them. And it's a Bogoliubov transformation, but adapted to physics. And later, the space-time has changed what we mean by particles. So it's not a choice that we make at the Scribe Plus.
Okay,
the space-time itself.
The energy of the system changed as well with that.
Exactly.
Okay.
So when the universe was older, it was hotter, right? And that meant that
Younger?
Younger. It was hotter. And that meant that smaller black holes were growing, right?
Depending on the temperature.
So
if the temperature was higher than the CMB temperature, they were not growing. So it depends on which black hole.
So the small primordial black holes, do we really expect them?
Yes, because as I said, at the beginning maybe the universe was too hot and they may grow, but the universe cools down and at some point they are able to emit.
Okay, so we expect it to be cool enough by the time they form.
Or a bit later. Maybe they start growing a little bit, but immediately or after some time the universe cools down and they can start emitting. And by now we should expect that. So.
Okay, thanks.
Any question? I mean, and that is the difficulty of in my opinion, good physicists are the ones who has the two grasps of mathematical things, and you are able to connect with physics. And Hawking did that. Hawking did this computation, and he was able to interpret physically, to put words to that. Because you can say, there is a change of basis, so what is the physics? No, this has physics on it. So the physics is that a black hole will disappear, will evaporate. That is completely physical. The black hole was before, and now it's not. So it's true that it's a change of basis, but that is induced by the geometry. The geometry tells you initially what is the natural notion of quanta, and finally what is that, and it happens in such a way that the black hole loses mass. More questions?
Why would the primordial black hole come to a stage of being hotter than the CMB? CMB is there for them too. Has been there for them too.
Right, but imagine that. Right, imagine imagine you start with a black hole with a very low temperature, and the CMB is hotter. So the black hole will emit, but will gain more than what it emits. So its mass will be growing little by little because it's absorbing CMB. But the CMB cools down, and there is, and there is a point in which the CMB is cooler than the actual temperature of the black hole. At this point, the black hole will start losing mass and from that on, we'll keep losing mass because it loses mass gets hotter, the CMB gets even colder, so and that happens.
Yeah, but that thing has not happened for the astrophysical.
No, and it will not happen in the age of another age of the universe or something like that, so, or even more. We will put numbers to the evaporation time to the second time. More questions? Zero. I never said that this is simple. Even people is still trying to understand what happens with Hawking radiation. It's having information with all that stuff. So this is a completely open field. But nobody doubts that these computations and the reality of radiation is a reality. That has been checked by extremely different ideas using different theories. Every time you try, Hawking radiation is robust. Okay, so now you want to go to the next section, which is generalization. And what I want to do in this section is to come back to our computation, look whenever we did an assumption, and see what happens.
I have a very quick question. Are the only small black holes primordial black holes?
We don't know of any other mechanism. We know one, which is
star collapsing is one.
Right, it's astrophysical, but
are big.
Exactly. You need the Chandrasekhar mass to produce a gravitational collapse, and therefore they are big. There is this idea that they are speculations, that gravity at large energies weakens, and because the coupling constant run, therefore people were speculating if LHC, the particle detector, could form black holes. Two proton colliding. If gravity is weaker, it's easier to form a black hole. Sorry, gravity is stronger because the coupling constant. I said the other way around. The coupling constant goes to and therefore, colliding protons, you could create black holes, and they could evaporate in less. So they were proposing that what you should see from collisions is not a few Higgs bosons or whatever, or jets going away, or couples electropositors, but you should see Hawking radiation coming from your collisions. You can see it. So, that of course that had the speculation that gravity has to become stronger at higher energies. But that is quite natural. There is a mechanism that if you have more than 4 dimensions and gravity really lives in a higher dimensional space, and we and all particles of the standard model, they are confined to 4 dimensions. So gravity is the only field which can explore the extra dimensions, and many theories that has that feature on them. Then gravity can be stronger than what we see at low energies. So, and it's a simple mechanism that produces that. So that is not a crazy idea. It's well motivated by higher dimensional theories. But it's a speculation. You have to assume that there are more than 4 dimensions in space. Normally, spatial dimensions. There are even theories with more than 1 time dimension. They are quite bizarre like that too. But normally all this, like a string theory, 26 dimensions, one is time like the other are space.
What other theories beyond string theory have large amounts of dimensions?
I mean, they are not theories at the same level as string theory. They are just models, just simple theoretical models that people try. There are many ideas that say, okay, let's assume that we live. I don't have full theory, but let's assume that we live here and we have gravity, and let's play around to see what happens. Okay, So I have several things I want to mention, if we have time. I don't know where to. Let me start with the second point that I have, because it's funny. 3.1, I want to talk about energy flags, backscattering, and gray body factors. Although, I am hesitating. So how many people is connected there?
Only Peter, and he lost.
Because I have to give those of you who are registered this evaluation, or my evaluation. Maybe today is a good time. Are you happy today with the class? And because the Peresek is not here, so I think we can take that. So I'm going to finish here, and we will continue the material next day. So what I want to do now is to see what happens when you include backscattering. Makes reference to including the potential in the wave equation. Remember that we were neglecting the potential. So what happens if you include the potential? And therefore, also I want to discuss what happens when using wave packets and how they are described and what is the result. And also what happens when you have a more realistic model of collapse, of formation of a black hole, rather than this artificial infinitesimally thin shock wave collapsing, just having a realized star collapsing. So how those results are modified, and you can imagine that they are not modified. So we'll do that next day, and then next day we will also discuss the implications for black hole thermodynamics. I already summarized them for you, so it will be a repetition. And what happens with this information paradox, what it is, and what people think. Then just a summary, because that can be a whole chapter or even more. And nobody has an answer, so I don't expect that I will give you an answer. I give you my opinion, but we will discuss that next time. Okay? So now those of you who are registered,